Okay, in class we talked about a toy problem where we're illustrating the idea of using configurable logic blocks from FPGAs to implement state diagrams. So in this case that we're studying here, let's do a one's hot implementation. And so with one's hot, we assign one flip-flop for every state. So we have 4 states here. So we'll have at least 4 of these assigned. And so let's work through it. In class, what we realized is if you don't have the right sort of split between the states, between X and next states, it might be harder to fit this into 4 CLBs. But I've modified the state diagram where I know this one actually fits within 4 CLBs. All right, so let's take this one at a time. The first one, let's take this to be state A. And so with state A, I'm looking at the one's hot assignment for the input for the QA flip-flop. QA is representing state A. So what I see from the state diagram is that the next state that lands on A is 1. You can land on A from A on X bar, and then you can also land on A from B on state B. So that'd be X bar QB. All right, and then I'm also seeing on X, I can land on A from D. All right, so I have 3 things that let me land on A. All right, so from that, I need to configure the configurable logic block. So we're looking at A, so I need the flip-flop. So I would choose, let me change this to red. I would choose the programming of bit 0 here to choose line 0 on the mux to include the D flip-flop. All right, so from there, I'm going to use the signal X onto the CLB. All right, so from there, I'm looking at when is X equal 0, that would program the upper LUT, and when is X equal 1, that would program the lower LUT. Okay, so let's break this into pieces. What is DA when X is equal to 0? Okay, so when X is equal to 0, then what I'm going to get is X bar is equal to 1. So 1 ended with QA is QA. And then I would also get QB. But QD, crucially, drops out of the problem. If I'd had another X bar there, this wouldn't have fit onto this CLB. All right, so when X is equal to 0, this term drops out, and we're just left with QA or QB. Okay, so from that, what that means is I can put QB here on the least significant bit and QA here on the most significant bit. And from there, I can say, okay, let's do a truth table, QA, QB. I need the order right. I need QA to be the most significant bit, QB to be least significant. Go through the combinations, and I'm looking at, okay, what combinations would give me the next states, QA or QB? So I know what the logic function OR is, so this would be 0, 1, 1, 1. And so to program that upper LUT, I would need 0, 1, 1, 1. Okay, now let's take a look at the lower LUT. Okay, so the lower LUT comes from DA given X is equal to 1. All right, because when X is equal to 1, you choose the lower LUT by the mux. Okay, so in that case, what you're left with is just QD. All right, and so I only need one input. I can have QD here. I can make this other one 0. All right, so if that's the case, then I never select this second column. And so really I'm down to just a 2-variable LUT table. And so I need to look at 0 and 1. These two would be 0 all the time. And so the upper positions on the LUT would just be 0, 1, where I'm programming in QD. All right, so here would be 0 and 1, and these would actually be don't cares, because if this is tied to 0, I can't access those lower bits in the LUT table. All right, so that takes care of QA. All right, let's do a similar thing for B. All right, so what I'm going to do here is take this whole thing, copy it, go to a new page. Okay, so from here, what I'm looking at is the next state for QB. All right, so I would look at the flip-flop input equation for B. And what I'm interested in, since it's one's hot, how do I land on B? And so it turns out I land on B from X on QA. It's this position here. That is the only arrow coming into B, so we're done. All right, so from here, I need to go ahead and wire up the flip-flop for QB. So that would mean programming this with a 0. Okay, and then I could use X as the control line on the mux. All right, so when X is equal to 0, I get 0 coming out. All right, so it turns out if I tied QA here and I tied this to be 0, actually I don't need to do anything. I can just tie, because this is always 0, I can just make this 0 and program a 0 here. Let me turn that to red. And the rest of these would be don't care. And the only thing I ever get coming out of this LUT, because the address lines are always 0, the only thing I get would be 0. Okay, so when X is equal to 0, I get 0 as the equation coming out. That would implement that. Okay, so when X is equal to 1, I get QA. So dB, when X is equal to 1, is equal to QA. And again, I could tie QA here, put this as a 0, and now I just have a one variable LUT table, because these positions are always locked at 0 if I tie that. So I would have that, and these would be don't cares, because I could never get down to, sorry, this would be 1, 1. I can never get down to this because this is tied to a 0. So these would be don't cares. And then QA is just 0, 1. All right, so I tie that to 0, 1, X, X. And this would program QB. All right, so let me paste again, and we'll do QC. I got too much there. That's okay. Let me do that again. Hang on. I'm going to come up here and copy the CLB and the state diagram so that we can get to it didn't work right. Let's move on. Okay, so from here, ignore this. We're looking at QC, all right? So the way I can get to C, so the input for the D flip-flop for the C variable state, for flip-flop QC, is I can get there from B, so XQB. I can get there from itself, X bar QC, and I can get there from D, X bar QD. All right, so let's break this down one at a time. 1 when x is equal to 0, where I use the upper LUT. Okay, so I'm going to do the same kind of programming where x is here. I still need to choose a 0 to get the flip-flop QC. All right. So when x is equal to 0, I'm left with just QC or QD. All right, so I put QD and QC here, and then OR would just be 0, 1, 1, 1. That's just an ORing of those two variables. Okay, and then for DC, when x is equal to 1. When x is equal to 1, I get just QB. All right, so as we did before, I can tie QB to this line, tie this to 0, and then plug in 0, 1, where I pass QB through the CLB. Those would be don't cares. Okay, so that's QC. And finally, let's do QD. Okay, again, I got some artifact things here, so ignore this, that's the QA equations that carried on with the paste. All right, so for QD, I'm looking at the input equation for D. All right, the way I can get to D is from C on X, so XQC. All right, that's the only arrow coming into D. All right, so since that's the only arrow coming into D, when I have x equals 0, I just get 0 back. Okay, so as before, I could just tie these address lines to 0. I would need to program then this location, because I'm always selecting that location, and the rest of these would be don't cares if I'm programming in, let me change that to black, the variable x, and we need QD here, and the flip-flop choice by programming a 0 here. Okay, so then D, when x is equal to 1, when x is equal to 1, we're programming the lower LUT. Okay, so with the lower LUT, I would just have QC as the variable. So I can put QC here, put this to 0, and as before, put 0, 1 to select QC. All right, and then these would be don't cares because I can't address those lines if I tie this to 0. All right, so that does it. That completely shows how you would implement this on 4 CLBs. You would have to route the signals in the correct way with the switch matrix on an FPGA to make X the controlling input, and you'd have to control, put the signals to the input LUTs. But this shows how the programming would work. All right, so this is a toy problem just to get you an idea of how programmable logic can be configured to give you different circuits.